Thank you. Let's see. We're going to use this one here. Okay. Well, I probably don't have to say anything, tell anyone in this room about the cultural and economic importance of salmon. We've covered that a fair bit already, so we can all stipulate to that. And I think we've also covered yesterday, especially, a little bit about the importance of temperature for salmon. Elevated stream temperatures being a pretty important threat to our salmon populations. And in fact, temperature is actually the most frequent source of water quality impairment in Washington. We've got hundreds of water bodies that have failed to meet federal standards because of elevated maximum temperatures or increased length of time when you've got temperatures that are beyond the optimal range for salmon. And really, that shouldn't come as a great surprise. Just about every single thing we do as humans in the watershed has the effect of raising stream temperatures. Forest clearing, agriculture, urbanization, all of that has the net result of making the water temperatures warmer. And as we've discussed, with coming climate change, that problem's only going to become much more severe and widespread. So temperature affects salmon at just about every life history stage. When you have the eggs incubating in the gravel, once the temperatures get to be greater than about 15 degrees Celsius, we see increased mortality rates. For the fry and the par, as they're growing, it affects their metabolic functioning. They don't grow as optimally. We see greater mortality rates there too as well. Ned talked yesterday a bit about columnaris. We see also that many pathogens affecting salmon, they become much more virulent at warmer temperatures. Again, that 15 degrees seems to be a bit of a cutoff there. And that has the effect that also affects the adults as they're coming back on their spawning migrations. When the water temperature is warmer, you see more pre-spawn mortality. We just see fewer of them making it to the spawning grounds to survive. So one of the tools that we have, jams before dams, one of the tools that we have to help alleviate elevated temperatures are engineered log jams in the river. So we've talked a bit about the importance of woody debris. It's sort of nice to follow Tim's work. Engineered log jams are things that we can build in the river that mimic some of the habitat effects of natural log jams. The engineering aspect provides a little bit more certainty regarding stability and function. The basic idea is something along, if we're looking at log jams to help create scour pools, for example, deep complex pools, the basic idea is if you have a somewhat flat, featureless reach of stream, you build a log jam structure that creates kind of a hard point that deflects the channel flow downward into the substrate, and that creates a bit of a scour pool, which then provides holding habitat for salmon. So among the habitat benefits that we see is this provides some energetically favorable holding water. If you've got all the root wads in there, that provides little nooks and crannies where the young fish can take refuge away from predators. But what I want to talk about today is the idea that these wood-formed pools can also provide what we call thermal refuge, some cool water refuge. In the river, these pools just have greater thermal inertia. There's a greater volume of water. It takes more energy to heat it up. And so those deep pools, especially down at the bottom, sometimes you get a bit of stratification, but they're much more likely to stay cooler throughout the summer, throughout the summer low flow period. Now, if we're looking at ways of combating the temperature effects of climate change, log jams can provide, fairly relatively immediate benefits compared to things like riparian reforestation, controlling carbon emissions. Those are essential, but those will take decades to start having any sort of effect. So at the same time, in the meantime, these log jams can provide some immediate relief. So for this reason, agencies here in the Nooksack Basin we've built a lot of log jams. There have been a number of projects with a number of structures that have been built all over the place, and I think Mike will talk about this in a little bit. But we're seeing some promising results here. So for example, these are data from one project where we've got a wood-formed pool, and let's see, is this the pointer here? Is that? No, that's a pen. Well, anyway, you can see that, here, I'll just use this. You can see that the water, it's okay, that's fine. The water temperature up at the surface of the stream, it's hovering around the 20-degree mark. But if you look down at the bottom of the pool at depth, you got much cooler water, around 14 or 15 degrees Celsius. So those pools, in some cases, they can be very successful. Now, this strategy can be especially effective if you can locate your wood-formed pool in an area that's receiving some kind of cool water influence. So maybe a cool mountain tributary that's coming in, or maybe some subsurface flow like a groundwater seep. If you can create that pool in that area, then that has a really good chance of providing a nice cool water refuge throughout the summer. But those cool water inputs, those tributaries, those seeps, those aren't necessarily going to be available or accessible at all of your project sites. So what I want to talk about today, my project, this is a long lead into it, is we're looking at the possibility of maybe using some of these log jams and these wood-formed pools to help create cool water refuge by actually promoting or enhancing some localized subsurface upwelling. And in particular, I'm talking about hyporheic upwelling. So, a little primer. The Hyporheic zone is a saturated subsurface zone. It's the area that's directly underneath and in some cases adjacent to the stream that contains a mixture of groundwater and surface water. That water has, relatively long residence times, but most importantly for our purposes here, it has a very constant flow and relatively constant temperature compared to the surface stream that you see up on the surface. And in many streams, most streams, we see significant amounts of water exchanging back and forth between the stream and the hyporheic zone. That's what we call this hyporheic exchange. And hyporheic exchange is driven more than anything by the bed topography, the topography of the stream bed. So what we typically see is if you've got, pools and riffles along your stream bed, we typically see water downwelling into the hyporheic zone at the tail of a pool, and then it'll move through the hyporheic zone through its flow paths, and then it'll upwell at the head of a pool. And that's generally how these things work. So if we can alter the bed topography in just the right way, perhaps we can encourage some more hyporheic exchange. So the idea then is if you've got a relatively flat, featureless run in a reach of river where maybe there's significant amounts of hyporheic flow moving through the gravel, you build your log jam, you get that scour pool going, and maybe we can capture some of that hyporheic flow, which maybe could have an effect of helping to help maintain those cooler temperatures in the pool. So that's the objective of this research project that I'm going to talk about. This is kind of a long-term project, and the idea is to see if this is possible. Can we use log jams to create these pools that'll actually enhance hyporheic flow and help cool those pools? The work is being done on the South Fork of the Nooksack, which is over here. South Fork is a good place for this kind of research. It supports 7 species of salmon, including a subpopulation of early Chinook that are considered essential for recovery of the Puget Sound Chinook population. And some of the key stresses that are affecting the South Fork are elevated stream temperatures and a lack of deep, complex pools. So, for example, talking about elevated temperatures in the South Fork, some of you probably have been tubing down on the South Fork. Probably none of you have gone tubing down the North or the Middle Fork because those are much colder, because those are rivers that drain glaciers, whereas the South Fork is fed mostly by snowfields, and so it gets much, much warmer. That's especially important for those early run Chinook. They're early run because they enter the river in summertime. They have to spend the whole summer in the river during that hot time of the year before they can get to their spawning grounds. And so in the South Fork, as you might imagine, the early Chinook populations are in some years very low, or in some years we get very low escapements. So this particular research is focused in a section of the South Fork that we call the Nessets Reach, which is about a 2.5 kilometer reach near Acme. And it's a site that I think it's sort of a good laboratory for this research because it's got relatively homogeneous bed topography. It's mostly runs and riffles with very few pools, but it has extremely hydraulically conductive substrates, and there's a lot of hyporheic flow moving through there. So this is the site of a restoration project being undertaken by the Nooksack tribe, where a series of logjam structures are going to be built. The basic idea is to take a run that looks something like this and turn it into something that looks more like this, where we have riffles and also more pools habitat. So structures are being built in a couple of different phases, and our research is following a sort of before-after control impact design, where before the log jams were built, we've consulted with the plans, we've identified the locations where we think those scour pools will develop, and so we've started to collect data in a 200 square meter area surrounding where we expect that scour pool to form, and then the idea is that after the log jams are built, we'll come back to the exact same location and collect our data once more. Sort of a before-after control impact, where we've got our impact plots where we're building the structures, and also some control plots where either the construction of the log jams have been postponed, or maybe they're not going to be built, but they're otherwise comparable. So basic idea there is we want to see how effective these log jams are at creating and affecting topography, hyporheic exchange, and temperature. So I'll just speed up ahead. So measuring bed topography, get out there with our survey levels. We can measure the bed topography before and after, and we can generate these kind of topographic maps for each of our plots. Then we can come in and measure hyporheic exchange. So for this, we use these devices, which are called piezometers, which are essentially it's just a length of PVC pipe with some perforations at the bottom. But we drive those in, and when they're in the ground, we can measure what we call vertical hydraulic gradient. And that's essentially just the difference in the water level with inside the piezometer relative to the water level in the surrounding stream. And if you have an area where the water level in the piezometer is higher than the surrounding stream, then that indicates upwelling potential. And you can also measure hydraulic conductivity, and you can get various other measures like that. So here's an example. Here's a picture. This piezometer is made of clear Lexan, so you can actually see the water level inside right over here. It's showing that this is an upwelling spot right here. So we can, so at each of our plots, we've installed this grid of piezometers spaced at 5-meter intervals. There's my student Matt standing around inspecting his work. And we can then overlay on top of those topographic maps, we can see where we've got upwelling potential and where we've got downwelling potential. And we can see how the plot changes in that regard before and after the log jams are built. Of course, it's not most importantly, we're also looking at temperature. So we've got a series of temperature loggers that we've put out at all of our spots. We've also taken some snapshots over a much finer grid to see subtle changes in temperature. I want to point out that these are the temperatures that we're looking at. We're expressing them in terms of relative temperature. So we've got kind of an arbitrary baseline at the USGS gauge at Saxon Bridge. And so we're looking at each of our fine temperature points, how they deviate from that baseline. So that way we can identify warm spots or cool spots. And that helps to account for, the diel and seasonal fluctuations that we'd see. So we can go back to our topographic maps with our plots. We can now overlay temperatures. We can say, oh, over here there's a hot spot, over here it's neutral, over here is a cool spot. And we can look at that relative to our upwelling and downwelling, and we can see if we're getting any upwellings and if those upwellings are indeed providing anything like a cool spot. So we take this combined with some snorkel survey work, so we can see fish use, whether the fish are using these plots, and that's the idea. We can then compare before and after the log jam. So we can use some geomorphic change detection tools to see how the bed topography has shifted in each of our plots. Then we can use some statistical analyses, try and identify some of the important factors that are driving the response variables, things like maximum temperature, upwelling potential, things like that. So in terms of results, well, I don't have any yet. But we've got a nice set of 4 years worth of baseline data. Some of the log jams have been built. In fact, most of the log jams have been built. We're going to be out there next summer, repeating our data collection, getting the first round of post-log jam restoration. Still have to figure out how I'm actually going to install the piezometers in some of those deep scour pools. If any of you have any ideas for that, love to talk to you about it. And while you're pondering that, I'll just say thanks to my collaborators with the tribe, all the students that have spent their summers pounding piezometers into the ground, swinging sledgehammers, and our funding agencies. So thanks.
Hi, I have a quick question.
Sure, Katie.
As stream temperatures continue to increase with climate change, could the thermal stratification of the pools affect the ability of oxygen to diffuse into that lower, cooler water and have impacts on salmon?
Yeah, that's a good question. Thermal stratification in those pools, as I understand it, doesn't happen everywhere. I think you need certain. It happens. We tend to see it more and more arid areas. It is possible that some of these pools could stratify. I think, but part of the benefits of these wood-formed pools is that they create pools, but you've got riffles immediately upstream, which provides a lot more mixing. And so what makes a really good habitat is when you have a diversity of habitats where you've got riffle, pool, and that provides more mixing. So good question, okay.
Yeah, so you'd mentioned that we have a lot of listings on the 303D list for temperature, and the log jams, I think they're going to be an important part of our recovery, but they're not going to get things off the list because we kind of base it on a natural condition. And at some point, we're going to need to figure out, like, how do we measure log jams as part of a natural condition? And so I don't expect anybody to have an answer today, but when you're out there working on it, if you can think, okay, how do we quantify how much is enough refugia and how much, what's a natural level of refugia, and start coming up with ideas on how we could quantify that. So when we go about setting a natural condition, we can say, yeah, this is natural enough.
Yeah, I think that's a good point. I mean, the log jams are not going to cool the whole river. That can't happen. But ideally, we can create a few little pockets of cool water where those fish can rest for a little while before darting on to the next one upstream. And in terms of how do we know when we have enough refuge in the river, I think, ultimately it's going to be when we start getting returns of salmon back that are, more in keeping with what we're looking for.
I was kind of interested in your use of, or how you're going to analyze fish use in response to logjam.
Yeah.
It's a pretty small spatial scale. Like, are you trying to look at like increased attraction to these log jams, and how are you going to reconcile that difference in like a really fine spatial scale of a log jam versus a spatial scale of like a juvenile in the whole stream?
Right. So this work is focused mostly on the adults as they're returning. So the data that we have in mind here is mostly through snorkel surveys, looking at how those those wood-formed pools are being used by fish relative to other habitats. So yesterday, I think Treva mentioned that in this year's surveys, something like 70% of the adult salmon we were seeing in the South Fork were associated with some of those human-built engineered log jams. Mm-hmm. And so that, to me, that's a good indication that they are being used, that they're important habitats for the fish.
Cool. So you guys are actually seeing like a significant response then?
Oh, well, oh yeah. I mean,
that's great.
most of the fish in the river are hunkered down in those log jams.
Oh, good job.
I'm talking about in the warm, hot summer period. Yeah.
Yeah. Cool.
Yeah.
Thanks.
Yeah.
I think that's it. Thanks.
Okay. Thanks.